Saxon's Trig, lesson 96, is about more double angle identities, triangle area formula, which of course you already know, proof of the law of sines, and then equal angles imply proportional sides. So part A, more double angle identities, says that we want to show, in example 1, sine of x plus cosine of x that is being squared equals 1 plus sine of 2x. Now, this goes back to working this side to get it to this side, although it could be whatever other method that you see. If it had been fractions, you would have done the cross multiply and so forth. But this one is what it is, and so we're going to square this side. Sine x times sine x is sine squared x. Sine times cosine doubled to 2 sine x cosine x plus the cosine squared x. And then sine squared plus cosine squared changes to a 1. That sine squared plus cosine squared equals 1 formula, plus 2 sine x cosine x. And we're trying to get to 1 plus sine of 2x. I want to make sure I don't have any errors here. Right, so this 2 sine x cosine x is actually one of the formulas for sine of 2x. So we're going to substitute 1 plus sine of 2x, and that is what they wanted us to prove. So check mark it. I don't feel like I have space to do example 2 there in the little corner, so let's change. Example 2, show that cosine to the 4th x minus sine to the 4th x all over top of cosine of 2x equals 1. Now, the first thing I see is that I've got a cosine 4 and a sine 4 in the numerator. I can probably factor that into 2 parentheses. So that's going to give us a cosine squared x and a cosine squared x. Same thing, no middle term, so 1 positive, 1 negative, oop, did not leave enough space, sine squared x, sine squared x over top of our cosine of 2x. Now, do I want to substitute that? No, I'm going to leave it at the moment. Okay. Now, I quickly see that cosine squared plus sine squared can be substituted as a 1, and 1 times this just means I'm keeping this part with the minus and the cosine of 2x. And I recognize that cosine squared minus sine squared is the same as the formula cosine of 2x. So now I've got cosine of 2x over another cosine of 2x. Same thing, top and bottom, simplifies to a 1, and that's what they wanted. Prove it. So check mark it. Now, part B takes you into the area of a triangle. Now, we know that an area of a triangle is half base times height. We also have learned that if we are not told the height, we can find the height by doing sine of whatever the degree is. Let's call it theta, and I'll label that theta. Is the height over the hypotenuse. So they would have to give me that, so that would be a b. And so then you're solving for the height by doing b times sine of theta. So what they're doing in this section B is they're writing out basically 1/2, and then if I called this one B and I had labeled, oh, I guess that's a theta, we'll call that one A. We'll call that one A then, and then this one would be a C. So the base would be C, and then the height we just found by doing B sine of theta. That was our height. And so the formula would be 1/2 CB sine of theta. Okay. I'm not going to memorize this because I'm going to stick with what I know, half base times height, and I'm going to stop and find all the parts that we need. So this is not technically another formula to memorize, although you could if you so chose. And I'm going to change one other thing here where I labeled that theta and I'm saying this is an A, this is a C. This would be capital A. So let's make this capital A here in the formula. And the reason I'm making that distinction is because if I take this same triangle and I flip it, and that means that I'm drawing the height to another location. So if I decide to call this one the base, then my height is being drawn in here. So I'm going to be getting half of, and the base then would have been A, and then I would get B sine of C if I stop and put all of those parts together. Now, why do I want to do this? I'm moving into section C, the proof for the law of sines. So if I have the same triangle and I just am flipping the base, and these are both of the area formulas, and I set them equal to each other, then we basically have half CB sine of A equals half AB sine of C. Well, on both sides I have a half, so I can ignore those. Both sides have a B, I can ignore those. And then if I decide to divide this sine of C over here, I've got C sine of capital C equaling, and this one had the A, and this one has the sine of A dividing away, coming to the other side. Oh, look, there's my law of sines. And by default, if I flip this triangle again and I did the other area, I could get the other part, which is going to give me the B over sine of B. So there is the proof that law of sines actually works. And part D goes into a reminder that equal angles imply proportional sides. So if I have two triangles and I choose to find, we don't usually work with the scale factor, but if you were finding the scale factor, in the one triangle, my side might be labeled A, and in the other triangle, A prime. And so the scale factor, that being the case, would be A dividing by A prime. And then it would work the same, B over B prime, C over C prime. Based then on the law of sines and this scale factor, I can say that scale factor is doubling for constant. So the constant is a match with A over sine of A. And that looks a lot like my law of sines. And so they're saying in that way, I am also proving that if I have two triangles that are similar, their sides can be set up in proportions because the constants form the fraction, and you would have a constant equal to a constant, so fraction equal to fraction. Why they choose to tell you all of that, I'm not really sure, but at least you have the information, and now then the proof of law of sines, which I said in the earlier video we would get to.